And today I will be your host for Machine Learning Study Jam Day 7. And our focus for today is prompt engineering techniques for language models. We're excited to have with us Pedro Gabriel, a Google developer expert in machine learning and the organizer for TensorFlow user group Sao Paulo. Pedro specializes in computer vision and natural language processing and is currently pursuing a master's degree where he is researching in diffusion models in biometrics. At Best Ever AI, he is the first machine learning engineer leading platform and product development. Pedro has contributed to several open source projects. Welcome, Pedro, and thank you for joining us today. We are looking forward to learn from you. And for anyone who has joined, please, it's requested to mute your mics, and we will be taking your question at the end of the session. Pedro will be answering any of your questions. You can write it down in the chat box, or you can keep them to yourself. By the end of the session, they will be answered. Over to you, Pedro.
Okay, thank you, Kaina.
You're welcome.
So, hello everyone. Thank you for joining today. I know it's Sunday night for you. So, yeah, thank you for joining. So, as Kaina said, today we're going to talk about prompt engineering techniques for large language models. You might know a lot of them, but there are like new ones that is more focusing for like reasoning problems that might be good to understand better. And yeah, but let's get started and see like through the talk. So yeah, so as kinda already presented myself, I am machine learning GD with focus on generative AI. I'm also senior machine learning engineer at Discover, where I'm working like with diffusion models and computer vision in general. I'm also organizer of TensorFlow user group in São Paulo, and I do a lot of like technical writing and open source contributions. So yeah, here is all my links. So if you want to connect to LinkedIn, Twitter, yeah, just go and get my links here. So the agenda today, we will start first like with a recap on how do large language models generate outputs. This will be like kind of important for what we're gonna talk, especially for the advanced prompt engineering techniques. So after the recap, we are going to cover the basic prompt engineering techniques, and then we will cover like some of the advanced prompt engineering techniques. The list is very long, and we won't have time to cover like a lot of them, but we will cover like the most used ones, and I think like that can make a very very good base for you to understand the other ones. And I will not only rely on this presentation, but I also have a collab notebook where we will be experimenting in real time these prompt engineering techniques. So I think it will help to become easier to understand the advantages and why it's working. Okay, so yeah, so okay, let's start with the recap. So how do large language models generate outputs? So the first thing we need to remember is that large language models are nothing more than next token predictors. And what I mean by this, so you basically you have your input, you pass this input through the large language model, and the large language model will output a vector of logits for you. After that, you apply softmax, and you get like the probabilities of like each of the tokens you have in your vocabulary. And the task of the model is to choose like to pick one of these tokens to become the next token prediction. And in this way, like you can, given your input, you can predict one token. But usually we are not like interested in a single token, but we want to like generate sentences. And how do we generate sentences using like large language models? So the idea is very simple. You basically like need to replicate the same idea of predicting the next token, like through a lot of different steps, but every time you predict a new token, you need to concatenate this token into your input. So in step 1, we predict like the token n plus 1. In step 2, we predict the token n plus 2. But like, look, we also like concatenated the token n plus 1 into the input to predict the token n plus 2. So this is important to keep in mind, because if you want like longer sequence, you need to concatenate more tokens too. And this is how we build sentences using large language models. However, there is one thing I didn't said. So if we go back to this slide, when we have the probabilities here or the vector of logits, one of the tasks is to pick. We need to to select one of these tokens from the vocabulary, and these tasks of selecting a token from this vector of logits or probabilities is what we call as decoding. And we have a bunch of decoding algorithms. So the easiest one and the simplest one is you just pick the one that has probability. So for example, imagine you start with Mari, and this is your prediction. So you have favorite with 40%, family with 20%, and name with 30%. So you pick favorite because it's the one that have the highest probability. And then when you predict the next token, you do the same. You pick the one with the highest probability. But not always you want to pick the one with the highest probability. Sometimes you need to make it more random. So you just rely on the distribution here, and you pick random one of these tokens. And another thing that is very important, and I think you might have heard this name, is the temperature. The temperature is a parameter that is used to control, let's say, the creativity of the model. So if you look on the left side here, we have the softmax equation. The softmax equation is the one that transforms your logits into probabilities. And if you see here, the Z1 is your logits. So we are dividing the Z1 by the temperature. So if the temperature is equals 1, you have your logits. So you basically this is the distribution you should have if you don't use the temperature in any way. But if you change the temperature, for example, imagine you make the temperature higher than 1. So you are making the logits smaller, so you are making the distribution, the probability distribution, more uniform. And what does it mean in terms of the prediction? So imagine you are relying on the distribution to pick the next token. So when temperature is equal to 1, you pick, most of the times you pick beer, because beer has a very, very high probability. So I don't know, in this case, let's say 6 out of 10 will pick beer. However, if we make temperature higher than 1, what happens that now you have beer and orange on almost the same level of probability, and also apple here. So 3 out of 10 you get beer, 3 out of 10 you get orange, and 3 out of 10 you get apple. So you are making your model generate more variety in the output, and this is very useful when we want to make more creative answers. And you can do the same with the opposite. So if you have the temperature of less than 1, lower than 1, what happens that you are put more you are increase the probability of high probable tokens. So beer will become much higher, and for example, apple will become smaller. So this is the idea. You can control the creativity and the I won't say reliability, but more the factual responses using this parameter. So and I won't dive deep into the decoding algorithms. There is a bunch of different ones, and if you want to know more, I shared 2 links here. But yeah, they are very, very important when you are dealing with generating outputs. But let's go to the prompt engineering techniques that is the goal of this talk. So for the basic ones, I will simply talk about them because they are the base for all the others. And the most simple, the one that we call as zero-shot prompting, that is basically you give your instruction and your input. So it's very straightforward. So imagine that you have this prompt: classify the sentence into neutral, negative, or positive, and you have the text, "We loved the movie we watched last night." And then you ask for the sentiment. You are not showing any examples. You are not giving a bunch of reasoning stuff. You are just saying instruction and your input, and you expect the model to answer this right. And why this works? It works because large language models, we know they were trained on large amount of data, which means like they learned a lot of different tasks and they encoded a lot of information. So if you ask, for example, for I don't know, some events that happens in when the computer was created, the model probably will know because it saw this in the training data. So this is why the zero-shot prompting works. And like why we should start with the zero-shot? Because it's very simple. We can try, and if it didn't work, it's easy because we didn't lose like so much time testing this. So this is the idea of the zero-shot prompt. And let me go to the Google Colab here. So a little brief context on this collab. We are using Gemini here. Here on the setting up the environment, we are just installing like the Google Generative AI library. That is the SDK for us to use the Gemini. And here we have like some imports, and this function to transform like let me show you, to make like the output a markdown, so you can see like in a beautiful way. And yeah, so we will run this. Here we are like configuring our API key to use the Gemini. If you want to know more, like you can follow this notebook, or you can just go to the like Google Gemini SDK Python, and you can just get like the get started with Gemini API or any other tutorial, and you find like how to make it works. Yeah, it's very simple. You just need to put your API key here and configure the GenAI, and then you can instantiate your model. Today we are going to use the Gemini 1.5 Flash, just because it's faster, so we can like experiment more. And so we have our model here, and let's go. I'm using the same examples of the slides, so because I just copied to there. So here we are asking to classify the sentence into neutral, positive, or negative. And when we run this, like we are asking here, the generate content is when we give the input to the model. So the answer was positive. As we expected, it worked like very easy for this kind of simple tasks. The zero-shot prompt is like almost always the one that we need to use. And then you have like the next version that is called the few shot prompt. The few shot prompt is kind of a zero shot with steroids. So it's very useful for complex tasks or new tasks where like zero shot doesn't work well. We leverage the in-context learning capability of the large language models. So what is in-context learning? Basically, like when you provide some demonstrations or some like explanation in the prompt, the large language models can use this to make better like predict. So it's very, very much important for when you are dealing with a complex task or a new task. And in the future prompt, what is the layout of the prompt you want to use? So basically, like, you want to give the instruction, and then you give to the model the question one, the answer one, the question two, the answer two, and then your input. So you are basically like giving demonstrations to the model on how it needs to think about it. So in this example, we are saying classify the sentence into this first class. You can see like I just typed like I just pressed some keys on my keyboard, so it doesn't mean nothing for us. So classify the sentence into this first class or the second class, following the examples provided. Don't provide any explanation, because the Gemini was providing like a chunk of explanation, so I only want like this first one or the second one. And then I will provide some examples. The first one, we loved the movie we watched last night. And the sentiment is like this first one. We as humans, we can understand that this is related to positive. Because the second one, bro, I hated the movie. The sentiment is like, is the second one, I don't know how to say. So we can relate this to the negative sentiment. But like, imagine that a large language model would never see these two concepts. It's a very hard task for it to understand. And then you provide your input and you expect like the answer. So let me go to the Colab. And yeah, so the first thing I want to show is without the few shots, so using zero shot. So we just say classify the sentence into this first one or the second one, and you provide like your input here. When you run this, what you got is like, okay, is this first one. Yeah, so we don't know, like, because we didn't provide an example. But like here, let's see, classify the sentiment into this one or this one. Okay, this one is positive and this one is negative. So we can see that the model answered right, but let me run like a few times more, because it was returning the wrong answer for me before. So let me show one thing. So if I change like the order, okay, it's still returning the right answer. Crazy. Yesterday it was returning the wrong one. Let me put that again. Or we can try like with a different class. Okay, look, right now it changed the answer. So like, yeah, it's basically saying that the model don't know like what it's doing, because sometimes it's returning one answer, sometimes it's returning the other answer. So imagine that like you want to make a real application for your company. This is not something you can rely, because the model is just like guessing, just like, okay, throwing a coin and get one of the answers. But like with the few shots, look, we are showing two examples. So one for the positive one, that is like this, that starts with L, and the other for the negative one, that is this one that starts with A. So we expect that this should always be the fourth class. So if we run this, let me run a few times. Let me put here so we can just see easy. So if we run this, let's say 10 times. So right, right, okay, right, right. So you can see that it's always like getting the right answer, because right now we provided some examples, so the model like figured out how to reason about like this input and the classes. So the few shot is very useful for these scenarios where you have like some not common tests and also like new ones. But you should, like, you might have asking yourself, so how many examples should I use? So there is no right number of examples. You need to try. Sometimes you like it works with 3, sometimes with 30, and like it depends on your use case. But one thing that you need to keep in mind is about the costs, because like when you increase the number of examples, you are spending more tokens, so you will pay more. So when you're like thinking about applications for companies, this is something that is important to keep in mind. So you need to find a good like balance between the amount of examples and the performance of the model. So, and this is few shot prompt. So if you like zero shot and few shot is what I'm calling as basic prompt techniques, because they are very straightforward. And if you have any questions, you can just type in the chat and we can discuss. Because now we are going to go to the advanced prompt engineering techniques. And when I mean advanced, I mean it's because like it requires more reasoning from the large language model, and also because sometimes it requires you to interact with different systems. So the first one we are going to cover is what we call as retrieval augmented generation, as known as RAG. So I think probably you saw these initials. It's being very used in the industry today, because like you can input your own documents, your like proprietary knowledge to the model, and like make the model answer given your documents. But let me explain like you in simple terms what is like the retrieval augmented generation. So imagine you work for a company, and you have a bunch of like internal documents. So for example, tutorials, you have like some meeting notes, a bunch of like this kind of tutorials, a bunch of this kind of documents that are very internal to your company. And you want to make an application that, okay, imagine that a new hire is starting the company, and like probably like they have some questions, and you want to make up an application where they can type the question and it searches through like the documents of the company and answer given this knowledge. So this is where the retrieval augmented generation goes, because like you have two options. You can fine tune the model to answer given these documents, but fine tune is expensive. Sometimes like you generate a new document every single day, so it doesn't make sense to fine tune every day. Or you have the choice to go like with retrieval augmented generation. So basically, like you need to have like all your documents indexed into a vector database. And what I mean by indexed, so you get all these documents, and you need to transform these documents into vectors, so you can search. So given a question, you can search which document have like the higher chance to answer this question. So the vector database is where you save these vectors. So here you have like all your documents indexed, and given the user input, you will embed the input. So you will create embedding for this input, and using this embedding, you will search like the closest, like the most similar documents into this vector database, and you retrieve like this document. So retrieved chunks is basically like, okay, imagine that you asked about like the meeting of the architect, the architecture meeting of a system. So it should retrieve like documents about this meeting or about this system. So we will have like a bunch of documents that is related to the question, and then you will make a new prompt using like the documents, and the documents will be like the context of your prompt, and the carry of the user that will be like the question. And given like the large language models have this capability called in context learning, the model will know, okay, this is the question and these are the documents, so I will come up with an answer for this, and it will like create a more like factual response, so with like less hallucination. And yeah. So it's very, as I said, it's very useful when you have like proprietary documents. It increases the reliability of the generated response, and today it's become an industry standard. So the layout of the prompt is basically like instruction, and you put like a bunch of documents. So like few shots, you can just test and see like how many documents you want to have here. So you put the document 1, the document 2, the document 3, and then the question of the user. So here's an example. I summarize it just to fit in the slide, but I will show like a real example in the Google Colab. So imagine that like this is your final prompt. So use the documents to answer the user. So you have like the document 1 and all the information of document 1, document 2, all the information of document 2, and the question, who were the authors of pi matching library? And then you expect the model to generate like this answer. Okay, let's go to the Google Colab. So this one will be a bit more code, because like we are dealing with different systems, but I think it'd be nice to see. So without bragging, our task, imagine that we are in a company and we have a bunch of like different repositories, each repositories, and we want to ask questions about this, like the code, some tutorials or some like, okay, how can I create a class of ta-na-na? So the idea here, you have like this big code base, and you want to make an application that answers given this code base. So my question is, who are the authors of pi matching library? So pi matching is a Python library, and yeah, you can imagine that like it's not like a very famous one, so probably the model won't know the answer. And we can see like here the authors were like Thomas Jarmer, Tobias Wellmer, Stefan Conrad, Stefan Harmelin. So when we ask like the Gemini to answer this without any knowledge or any other information, just like a zero-shot prompt, this is the answer. The PyMatch library doesn't have a single set of authors, but like we saw here that they have the authors, so it just returned it like just like hallucinated about the response. So if we run again, oh, it's saying that it was, but if I'm not wrong, it was developed like by some like university students. So yeah, not a double research. So you can see that it's hallucinating. It's answering, but like it's not the right answer. So how do we make like a RAG application? So we will need to install some stuff. So sentence transformers here is to like transform a document or like a user input into an embedding. Fast CPU is a way to create like a vector database in memory. So we need to install. I already installed this because it takes a bit of time. Then we need to import some of the important libraries. Here is the documents we will use. So you can see here, like I'm just getting the README of some. Like this is the README of the transformers library from Hugging Face. I'm just getting the markdown. Like here is the PyMatching, the one that we saw here. I just copied the markdown here, and here is the one from YOLO. Yeah. So just for an example, I'm downloading this. So you can see that it's creating like this folder called readmes. Then we have like some helper functions. So this one is to help us to split the documents. So I won't deep dive on this because yeah, we don't have so much time. But basically, like I'm splitting the README into chunks of 1,000 tokens, 1,000 characters, to be honest, and with an overlap of like, imagine that you have a sliding window, so we are 1,000, so we start like 0 to 1,000, then we go to the next one, will be like 200 to 1,200, so because like we want to have some overlapping, it's very useful when you don't want to like to break some sentence in the middle. So when you create some overlaps, like it's a way to deal with this. So we are like splitting our documents, and then like here we are creating the embedding. So if you see, this is all chunks is how many chunks we have. So let's see the length. So we have 91 documents right now because we split it. And then we will create the embeddings for all these documents. So we are using the Mineral. It's like a very, very light encoder. So you can see we are running on CPU and it runs pretty fast. So let's wait. And don't forget, like we have 91 documents. So when you look to the shape of the embeddings, we have 91 rows with 384 columns. So this is the dimension of our embedding vector. So all of 91 documents were embedded. And now we need to create the vector database using FAST. So we basically like say the dimension of the embeddings. We create the index and then we add all the embeddings. So it's very simple. Now we have like our vector database. So if we go back to this image, we build like this part here. And then we need to build our RAG prompt. So the user question is, who are the authors of PyMatching library? Now what we need to do, we need to transform this into an embedding and search, like here I'm searching the 5 closest documents to this input, and then we will build like the prompt in the same way I show it here. So instruction, document, and the input. So yeah, basically like the relevant documents, we add all the documents and then we build the final prompt. So I will run this and let me show you the final prompt. So this is what like we use to call the model. So let me just print because it's easier to see. So yeah, use the documents to answer the user. Relevant documents, doc4, and then we have like the doc4 here. Doc3, and this number here is like the index of the document, just this, nothing more. So document 3, and we have like the document 3 here. We have like, I think it returned only 2 documents. Yeah, because the other ones, probably they were one more. Doc2, we have the doc2 here. Yeah, so we have doc 54, we have doc 54 here, a bunch of stuff. And then we have the question the user made, so who are the authors of by matching? And when we check this is the answer of the model right now. So the authors of the by matching library are Thomas Jarmer, Tobias Wellmer, Stefan Conrad, and Stefan Harmon, the ones that we see here. So now that we provided some external knowledge to the model were able to generate the right answer without hallucination. So this is the magic of the retrieval augmented generation. So, and you can replicate this like using your own documents, and you see like how much and how easy is to make it work. Yeah, so I think like this is what I have to say about augmented generation. Here's like one reference if you want to know more about different like experiments, like changing the vector database, changing the sampling strategy. So you can check here. It's very nice. Okay, so the next prompting technique I want to talk about is this thing called chain of thought prompting, and this is the initial. So COT. This is the, like, I think when you see on some LinkedIn posts or papers, this is the way that you see it. So imagine that the standard prompting for, let me just give you a brief context. So it's very useful for math problems and problems that requires more reasoning. So when the model needs to create like mental relations between different entities of the prompt. So let's go like to the standard prompt. So imagine like this problem. The cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? And the model answered like the answer is 27. Just another hallucination, because 23 they used 20, so they had only 3, and now plus 6, so the answer should be 9. And like we gave like some demonstration to the model, but like this is not enough for this kind of problems that requires reasoning. We don't need to only show the answer, but we need to show like how to think about the answer, how to come up to the answer. So if you see here, the difference is now that on the demonstration we are not only showing the answer, but we are showing like the reasoning behind the answer. So this was the example. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And before we just said the answer is 11, and now we said Roger started with 5 balls. 2 cans of 3 tennis balls. Each is 6 tennis balls. 5 plus 6 is 11. So the answer is 11. Look, now we are saying to the model, okay, you need to pay more attention on the reasoning process to create the answer. And when we ask the same question we asked before, now the model output is like the cafeteria had 23 apples originally. They used 20 to make lunch, so they had 23 minus 20, so 3. They bought 6 more apples, so they have 3 plus 6, 9. The answer is 9. So now the model like can come up with the answer, which is quite nice. So it's basically like a few shot prompting with steroids, and it's very, very useful for complex tasks like math problems and reasoning problems. So the layout of your prompting should be like the instruction, the question one, the reasoning of the question one and the answer of the question one. The question two, the reasoning of the question two, answering the answer of the question two, and then input. If you want to add more demonstrations, you can. It's just like the trade-off between the amount of tokens and the costs. And here's an example. So you have like the question. This is I will show you on the Colab. Then you have like the answer, and the answer here is like the explanation, the reasoning, and again the answer. Then you have like your input, and you expect the model like to reason about your question and come up with the right answer. So going back here, I have the same idea. So without the chain of thoughts and with chain of thoughts. So let me just put this here. So the question is, 2015 is coming in 36 hours. What is the date, 1 week from today in, like they want to format the date in the right format, and they want to make like this relation between, we know like the 2015 like will start in 36 hours, so like the model needs to reason about this problem to come up with the answer. But like this first one, we are not providing any explanation. So the answer is 01/05/2015. And then we put our question. The first day of 2019 is a Tuesday, and today is the first Monday of 2019. What is the date today? So here, just to say, we expect the answer to be this answer here, because today is Tuesday, and no, today is the first Monday, and the first day was Tuesday. What is the date today? So the first day was Tuesday, so we need to like walk more 6 days to go to the Monday. So it's day 7. So the model provided some explanation, but it's just an hallucination because like it's wrong. The day should be like 7 and not 8. And then we go with the chain of thought. So instead of just providing the answer for the first demonstration, we provide the explanation and also the answer at the end, and we ask the same question to the model. So yeah, as you can see, now the model answered right because it's paying more attention on the explanation. So this is the idea behind the chain of thought. Yeah, so and last, like this is the last prompting technique we will see today, is self-consistence. Self-consistence is like a chain of thought with some steroids. Instead of like just simply one answer, we have our prompt, we send this prompt to the language model, and then like we sample, I don't know, 3, 5. You choose the amount of answers you want to sample, and okay, you do like different answers here, and given all the answers, you get the one that is more consistent. So you can see like from 3 answers, 2 of them said the answer is 18 and 1 said 26. So what we do, like we aggregate this answer and we get the most consistent one, so the one that appeared more, and we get the answer is 18. So it's a way that with really hard tests, it's a way you can deal with this. So as I said, is the chain of thought with steroids. You sample multiple and diverse reasoning paths and select the most consistent answer. So temperature is very important here. You can like tweak the temperature to see like how the model performs for your experiments. In this case, I used 0.5. So yeah, it worked for me because like I gave more. I make the model like hallucinate less because when you like make the temperature hunt, you make it like more uniform, so it's more creative. And when you make like less than 1, you make the model like less hallucinated. So I choose 0.5 here. And if you want to use in real world applications, you need to keep in mind the amount of tokens you will generate, because now we are generating like three or four or five different answers. So you pay more for this. So you always need to think about the costs when you're dealing with applications for real world. So let's go to the local lab here. So this is the prompt we have. So the question is it's a question about inequality in math. So I won't read, but you can read by yourself after the talk here. So we have the question, and we have the first answer, and the answer is the reasoning, and at the end the answer, and you have the question itself. So we are asking the product of three positive real numbers is 1, and their sum is greater than the sum of their reciprocals. How many of them can be greater than 1? The answer should be only 1, but you can see I ran this before. The model answered okay. At the end the answer was there can be at most 2 numbers, which is wrong. This is the wrong answer, and this is how we do with the self-consistency. So I'm creating the generation config here, and I'm asking 5 times the model the same prompt. So I will run this, and here I will just print the responses for you, so we can all see and we can make the aggregation by ourselves. So yeah. Oh, sorry, I didn't run the prompt here. So yeah, it's taking more time because the answers are a bit longer, because there is a bunch of steps, as you can see here. It should finish in a minute. So look, I make a small parsing here. So this is the first answer. 2 of the numbers can be greater, so it's wrong. Only 1 of the 3 numbers can be greater. Yes, this is right. Therefore, it can be at most 3 numbers. Wrong. Only 1 of the 3, it's right. At most 2. So you can see it made the guess right 2 of the time. So if we increase 7, we can just increase the amount of examples to see to make the aggregation more reliable. So this is the idea behind the self-consistency, and this tweaking between the amount of generations, the amount of the number of demonstrations. This is something you need to do when you are doing experiments. It's very important because for some tasks 3 can be a good number. For some tasks 15 is the best number. So this is something important when you are experimenting with the model. But yeah, that's it. I think if you have questions, okay, let me just see here. So 2 numbers, 1, 1, 3, 1, 1, 1. So right now we can definitely say that 1 is the right answer, because I think 5 out of 7 answered 1. So you can see now we have a much more reliable answer. So this is the importance of the self-consistency. And yeah, just to finish, as I said, I covered just a small portion of the prompt techniques. As you can see here, there is a bunch of every day a new one appears. So I put on this slide a reference for a survey. I think it was from the last week, that tries to summarize a bunch of the newest prompt engineering techniques. Some of them requires interaction between different large language models or different systems, but some of them are simple. But I think it's worth it to see. Just if you have if a problem, maybe you should answer on how to solve. So yeah, that's it. I wish you feel, and also the Google Lab can try by yourself. So thank you so much, and feel free to ask any questions you have.
If anybody's got any questions, they can ask Pedro regarding it, and you can unmute your mic and ask your questions. Okay, I think nobody's got any questions. So, Pedro, thank you so much for your time and all of the expertise that you have shared here. And I hope everyone found it very valuable. And thank you so much for all of your time. Thank you.
Thank you.